We'll continue where we left off yesterday. We were talking about number representations and essentially trying to see what are some ways by which we can represent fractional or real values in binary. Okay. So the idea is very simple. We know how to represent integers. So this would, for example, in binary correspond to the number 106 in decimal, right? So this notation, basically putting parenthesis and then indicating the radix as a subscript, is sometimes used. It's not very common, but it's a simple way of indicating which radix we are using, okay? And I'll be using that if I want to distinguish between which base or radix I am using at a given point in time. So this would be an integer. A real value would essentially involve introducing a decimal point or a binary point somewhere in this number, right? So I'm going to use the term decimal point, binary point, or just point interchangeably, right? It should be clear from the context that all I mean is basically, the position of the dot that separates the integer part from the fractional part, right? So for example, if I wrote it like this, this would essentially correspond to 6.625 in decimal, which is basically equal to 106 divided by 2 power 4, okay. So the same value, essentially the correspondence between these two is directly because of this connection, the division factor over here. Now in terms of terminology, what we say is this is sometimes called the integer part and this is the fractional part. Okay. So we would like to use both of them, the integer part as well as the fractional part, in order to represent numbers. Now there are a few things that come up as a result of this particular choice that we have made, right? One of them in particular is, what is the range of numbers that I can represent by doing so? Dynamic range, essentially what it's asking is, what is the range of values that can be represented using a given notation? And by range of values, we want to make it clear that I don't care about positive versus negative. I'm talking about, let's restrict ourselves to the positive part of this notation, right? What is the smallest positive, not non-zero number that I can represent, and what is the largest positive value that I can represent, okay? So let's look at integers. Smallest positive number is 8-bit integers, okay? What is the smallest positive number? 1, okay? Largest positive? 127, okay? So the dynamic range is basically defined as 127 divided by 1, it's equal to 2 power 7 minus 1, okay? If I look at the negative values, it would basically be exactly 2 power 7, that is the range, right? The difference is small enough that I am not going to bother about it. I am just going to say 2 power 7, in fact, as the dynamic range, okay? Now what happens to 8-bit 4.4 numbers? What is the smallest value that I can have? 2 power minus 4. Largest was that 7.9 something, which if you remember was actually equal to 2 power 3 minus 2 power minus 4, right? It is basically 8 minus 2 power minus 4. No, I have 4 bits for this one, right? I am talking about this notation over here, this value. So it will be 8 bits, so there will be 4 bits before the decimal point, maximum value can go up to 7, so 2 power 3, right? So 2 power 3 minus 2 power minus 4. Once again, dynamic range is 2 power 3 minus 2 power minus 4 divided by 2 power minus 4, which is exactly equal to 2 power 7 minus 1, right? So this is sort of just once again stating what should have been obvious to you from the beginning, the dynamic range that we get for 8-bit 4.4 numbers does not really depend on where the decimal point is placed. Whether it's 4.4 or the 8-bit integer could be considered as a special case, an 8.0 format, right? 8 bits of integer, 0 bits of fraction, right? So an 8.0 format, 4.4 format, 2.6, 1.7, all of them represent a different range of numbers. The actual maximum will be different, but the ratio of the maximum positive to the minimum positive will always remain the same. Okay, and that's just determined by the number of bits that I'm using. Okay, so effectively what we are saying is, when I use 8-bit values, in other words, I get a range of 2 power 7, a dynamic range of 2 power 7. Okay, so if I wanted to extend this and I asked you the question, 32-bit, this is essentially what I refer to as fixed point numbers. I am just going to ask you 32-bit fixed point numbers. What's the dynamic range that I can get using this kind of notation? 2 power 31. I am ignoring the -1 because it's very small compared to the 2 power 31. The important point is that the 2 power 31 is the actual ratio of the largest positive to the smallest positive number.